Alrighty everyone, welcome back. Today is Wednesday and today is our second day of quantum mechanics. So we're going to do some review and talk about wave functions, and let's see, we're going to also cover some mathematics as well. So with that said, sorry, my effects guys are here. Hey, what are we doing today? How about a cat, right? So let's have it like a cat walk in, right? Okay. What did you do? Okay, all right. I guess that's where we're going now. Get out of here. Moving on, all right, why don't we just get into our review of what we covered on Monday, which we started out talking about Einstein's theory of relativity, the real equation, the one that the government's hidden from you in all those libraries and textbooks. And I'm not going to write that one down, but what Einstein was able to do with the theory of relativity was show that photons that we just think of as having wavelength also have momentum, which is how the photoelectric effect was described. But de Broglie, won the Nobel Prize in '37, kind of turned it around. It's a little bit more complicated than this, but basically turns that equation around and says, well, things that have momentum have wavelength. And cool, all right, let me just remind you, P is momentum, that's mass times velocity, and don't forget that a lot of these old geezers were, I shouldn't say geezer, anyway, they were all physicists, and physicists don't like 1/2 mv squared. They like p squared over 2 Wenham for kinetic energy, and that has the proper units, but whatever. So we just want to get used to that. It is 1/2 mv squared. All right. Schrodinger then takes the equation, which I mentioned. This is the right equation for musical instruments. This is the right differential equation that describes standing waves, right? Yep. You guys know you're nerds. I know you played violin in middle school, right? And so, of course, back in the day, they were interested in mathematically describing, standing waves, which is how your piano and stringed instruments work. It's actually how wind instruments work, too. It's just the wave is an air wave, right, as opposed to a metal string. And so that's basically what Schrodinger used. He just used the same equation for standing waves. A little bit more complicated, but for now that'll do. So we have double derivative. This ends up being kinetic energy, and we described that last time. I won't get much into it. We have potential energy times the wave function and energy times the wave function. So notice that it has the form of the differential equation where we have a double derivative here times a function. We're going to just make potential energy 0 for the next 2 weeks because it's just easier that way. And the function has to, basically I use this kind of crude description. The wave function, you take the double derivative, but it boomerangs back. And when it boomerangs back, it's multiplied by a number which happens to be the energy. And the energy will be in joules, and the units work out and all that jazz. So anyway, so notice that this is not a problem specific to the Schrodinger equation, yet the Schrodinger equation is a differential equation, technically a second order differential equation, that you have to operate on this function, and yet the function still comes back. And so that ends up being where this is a really tall order in terms of the mathematical complexity. Now, I already mentioned that I will show you a little bit about how mathematicians solve this. It's not required. I'm just going to show you on an extra Friday, just so it's not like a mystery, right? But this is not math class. So that's not part of this class. What I'm going to do is I'm going to do what I did last time, which is to give you an obvious answer. Remember, when we have differential equations, the answer to the equation is a function that makes the differential equation work. In our world, that's a wave function. I started out with cosine 2 pi x over lambda, where x goes from 0 to the wavelength lambda, then cosine goes from 0 to 2 pi. I know I try not to speak equations, but I can't resist. And then I said that, let's just call that cosine kx, where k is 2 pi over lambda. Remember, that's called a wave vector. Remember that tells you the direction that the thing is going in. And we used our little Schrodinger equation to show that k is square root of 2m e m is mass over h bar. We also showed that this is completely consistent with the de Broglie relationship. So there you go. That's really all that there is to it. We're going to spend a lot of time interpreting the next week, just interpreting all of this mess. And then we build more complex models. Now, initially, the potential energy will be 0. And you notice I put a little hat. That means it's an operator. Now, what that means is, let me give you an example of another operator so you understand what it means. This is the kinetic energy operator. So that's sometimes I can call that like KE with a hat, and this is potential energy operator, so V with a hat. Notice that I have E but no hat, right? Now that's because, let me give you some math language. Again, not required. I just want you to know this kind of stuff because, you know, STEM, college degree, you should know these things. E is a scalar. Fancy word for a number, like 1 joule. Operator, now I'm guessing you've seen this for the first time. It actually means, well, let's look at kinetic energy operator. It is operating on a wave function. It's changing it, right? Isn't that what operate means? It's taking the wave function and spitting out, chewing it up in the form of a double derivative and multiplying it by some constants. That is what it means to operate. It just means change it. Okay, potential energy. Let me preview a bit. You know I do a lot of that. Okay, what's potential energy going to do? Well, potential energy could be something like the potential energy of a spring. What's that? That's 1/2 kx squared, right? 1/2 kx. K is the spring constant. 1/2 kx squared is just a harmonic potential, which is what we use to describe springs. Why am I describing a spring with the Schrodinger equation? Because that's like a chemical bond. We think of chemical bonds as springs. Now, what happens is, we're going to get to chemical bonds, and we're going to have 1/2 kx squared. And what that's really doing is taking the wave function and basically multiplying it by some constants times x squared. So, cosine is cosine, but x squared times cosine is not cosine, right? Cosine is change. Cosine x is change if you multiply it by x squared. X squared cosine is not cosine, right? Pretty simple. So potential energy ends up kind of being an easy operator. Heads up. It's the kinetic energy operator that makes quantum mechanics as difficult as it is. Last thing before I get into some real material. I know that this is subtle. Probably no one's noticed, which is fine. But let me point out, all right, kinetic energy, double derivative. Now that's kind of weird, because what I normally think of, I think of my cat Charlie. She's my second favorite. I don't think she's watching, but here's Charlie. She's got a little smug look on her face, which is what? Sorry. Anyway, you know what she does? Every night, she goes ballistic because she's a cat. She runs around like crazy, just like will not stop. And then she runs to the tallest place she can find, and she looks down at me and she does this. Just like that. Okay, so that's kind of actually captured that quite well. Okay, so let's model Charlie's kinetic energy. Now, the way I would do that is I would have some path, and I'd have some path as a function of time. I put X, didn't I? Some path is a function of time. Now, I would know that this would, say, describe the position. I would then calculate the velocity by taking the derivative of the position with respect to time. And now I have velocity, and if I wanted to get the acceleration, I would do the double derivative. And then I'd multiply by Charlie's mass. She's kind of small, she's only 9 pounds. Now I have mass times acceleration, and now I've got force, and then if I know how far Charlie travels, then I know how much energy, right? Force times distance. Okay, double derivative. So let looks like I've got the same thing that you've always known, but look, I've got the position as a function of time, and I'm doing a double time derivative. Here, I'm doing a double derivative, but not in time, but position. Right? Why would that make sense? Why would that be related to kinetic energy? I get velocity, I get acceleration. Those are related to kinetic energy. Why would the double derivative with respect to position instead of time? Why would the double derivative of position be energy? That's where this gets strange. Now, I don't, I've been doing this for years. I kind of get it, and I think I get it because I've seen it so many times I accept it. That works, right? But if you're looking at this and just are kind of confused, that's okay, because you know what, let's just do problem after problem after problem, and maybe you'll accept it just like I do. Anyway, I just wanted to point out that's just a way that this is weird. Okay, now as I mentioned, that we're going to spend a tremendous amount of time doing, like interpreting what we've seen. All right, so let's start with the wave function. Okay. What about wave functions? Now, wave functions, unfortunately, you need to know this. I hate this stuff. They have 3 names, all right? So we already know that they are wave functions, and I'm sure you've heard that before. Let me just type wave function. They have 2 other names. They have 2 other names, eigenfunction and eigenvector. Okay, now I will occasionally use either 3 of these just because it's just going to fall out of my mouth, because these are all 3 words for the same thing, and I don't know how my brain picks one, but it does, and it's never the same, so heads up on that. Okay, when it comes to eigenfunction, eigenvector, that comes about from the eigenvalue equation, which is, we often like to describe the Schrodinger equation. Let me write it over here. We often like to describe the Schrodinger equation this way. What happens is you can factor out these operators, and let's call that H, let's call that one operator. It stands for Hamiltonian, by the way. And here's the wave function, and it's equal to the energy, no hat because it's a number, times the wave function. Okay, so that is an eigenvalue equation. It's an equation because it's an equation. Usually you see an equal sign. The eigenvalue, by the way, that's the energy. And it's an eigenvalue equation because you have the wave function on the left and on the right, like any differential equation. Okay, so if this is an eigenvalue equation, then the solution is the eigenfunction or eigenvector. Right. Now the word eigenvector I'll explain a little bit more. That'll make more sense. Anyway, okay, so those are the words. All right, now here's the thing. You could imagine that the wave function spits out energy. Okay, what's that good for? It's good for spectroscopy. A lot of this got started because, for one, people had electricity around 1900. They started making vacuum chambers. They were able to isolate elements, right? You can isolate hydrogen rather easily if you have current. Just stick it in some salt water. Out comes hydrogen. Put hydrogen gas in the spectrometer, or maybe I'm doing the deal. Okay, inside the spectrometer, bleed in gas and make an arc out of electricity. What do you get? Hydrogen atoms. The hydrogen atoms are the excited state, and they start to fluoresce, and you measure the fluorescence. There you go. Around 1900 to 1920s, everyone got obsessed with understanding the fluorescence of hydrogen atoms, right? They knew that this is something they should be able to understand. No one did, so this is what people worked on. It turns out that the energies, Schrodinger's first paper was on the hydrogen atom. He listed all the energies, and the differences in those energies corresponded to the spectroscopic observables, and he got it right. Okay, so, cool, and that's what got all of this started. But what about the wave function? Here's my point. Does it mean anything, or was it a useful tool? Was that it? No one really knew, but Born, and this is not like Born's law, it's called Born's, I have to write this down, Max Born, kind of an awesome name, isn't it? Max Born, his interpretation. So I'll use some shorthand there. You're going to love this, actually you may hate it depending. Okay, let's take the wave function, let's take the absolute value, and then square it, and guess what this is? This is a probability density. Right, that thing we just did a few weeks ago. Maxwell-Boltzmann, this and that. It's back. Right, now you see why I do Maxwell-Boltzmann stuff first? Because it's a warm-up for this. Okay, the absolute value of a wave function squared is a probability density or a probability distribution. What's it the probability distribution of? Well, it's a function of position. So therefore, I interpret this as where is the particle? If the particle is Charlie, where's Charlie the cat? The absolute value is the probability of finding this particle within whatever the limits of integration are when you're doing stuff like this, right? So let's take average position, and you're hopefully, advanced enough along after this amount of time. We haven't had a lot of time, but hopefully you know that the average position would be the integral over all possible values of the wave function squared times the thing you want the average value of. Okay, so now you see how to use it, which is exactly what we had before. Now notice that you can also, just like Maxwell-Boltzmann this and that, oh, I'm writing over my equation, sorry. You can also do stuff like this. You can get the average of the square, because why not? Actually, this ends up being really important in about a month. So put a tag in that. And, okay, one last thing. Now, I hate to break the fourth wall here, but on your final, you're going to have Maxwell-Boltzmann equations, you're going to have quantum equations, right? Here's the thing that a quarter of you will drop a grade for. Swear to God, I've done this 10 times, right? I know. Maxwell-Boltzmann gives a probability distribution. You just do it. Wave functions have to be squared, and then you do whatever your average value is. Where do people drop a letter grade? They take a Maxwell-Boltzmann distribution and square it. No, it already is a probability distribution. It's not supposed to be squared. Or they take a wave function and they don't square it. No, the wave function squared is a probability distribution, not the wave function. Don't forget that. Although a quarter of you will, because this happens every year. I say the same thing. I've been saying the same thing for 5 years, and no one listens anyway. Where'd that dinosaur go? All right, so if you get confused about what I just said, let me point this out. Let me just draw a wave function. This is like the Charlie wave function. Is this the right? Yeah, okay, it's the right word. Okay. Here's the wave function. Here's the position. Oh, and that's not an X. I messed up now because I kept writing T's and now I'm writing X's and now I'm getting confused. Anyway, a wave function can look like anything. So I'm just gonna make something up. Here we go. That looks fine. Why not? Okay. Notice why this thing cannot be a probability distribution or probability density in its own right. Because it can be negative. It can be anything, almost. But probability densities can't be negative, right? Because that means that over certain regions, if we integrated over this region, then there's a negative probability of Charlie being at that region. No, there's no such thing as negative probabilities. Okay, so here's what you do. You square the thing. So let's take that, and I'm going to graph the same thing. I'll dash this. And it kind of depends whether the values are higher or lower than 1 when you square them, whether the square is bigger or smaller than the resulting function. So I'll just say that it's bigger. Okay, but the one thing it is not negative. There we go. All right. Now when you integrate that, of course, you're going to, over some region, you'll get a positive value. And in fact, if you do this, if you integrate the wave function, oh, that looks terrible. Looks like a messed up 4. Okay, if you integrate over all values, you better get 1.0. That means that the particle is somewhere. Just like the argon, atom has some velocity or no velocity. It has some energy or no energy with a probability of 100%. This particle is somewhere. I'm certain of that, right? So we can read these off like we're 5th graders. Okay. Now this, remember that I told you this is called normalized. And let me preview a little bit about some of the difficulties we're going to have. When it comes to solving problems, it turns out that figuring out the wave function is not difficult at all, because almost every example we're going to do early on for like a month, it's always a cosine or a sine. So we can look at the problem and just say, oh, okay, well, the wave function is sine or cosine. Right? Now remember, I warned you that early on this would be kind of deceptively easy. Mathematically it will be easy. The interpretation is a little difficult, what you're seeing right now. Okay, so what? When you kind of just figure this out without even using the Schrodinger equation, you can do that, but you don't have to. And again, you're going to see that I'm previewing. It isn't necessarily normalized, so be careful about that. Now, I'm going to introduce this concept formally in next week, but I'm just going to go ahead and tell you now. Often we figure out wave functions outside of the Schrodinger equation. Cool. But they're not necessarily normalized. So you have to, once you figure out what a wave function is, you have to double check that it's normalized. It almost never will be. And then you figure out what, you just multiply it by some constant that will make that true, right? So all those constants, that Q that I kept moving outside of Maxwell-Boltzmann, now what you do is you figure out what those constants need to be. You have to add them to the wave function such that the wave function squared integrates to 1. Anyway, you're going to see lots of examples of that. Okay, let's see, we're making pretty good time. Now, on your first homework, you had some mathematics problems, which I did to force you to do it. But as the homework sets go on and on and on, and I've been doing this for a pretty long time, as I craft those problem sets, what you see are problems that are coming in the future. Kind of like that movie Tenet, which was awesome, I just saw that. Anyway, so the problems you see are sometimes solutions to problems you're going to be getting in the future when we get more into quantum mechanics. So in the case of your first homework, you may recall, let's see here, what am I doing? We're going to get into complex mathematics. So I told you all about wave functions and the Born interpretation. Now we need to do a little bit of math, this and that. I want to make this a wave function. And heads up, this is the solution to what, sorry, let me helps when I turn to the camera, right, to hear me. This is often the solution to many, many quantum mechanical problems. But notice that, unfortunately, I'm dealing with some complex mathematics. In fact, that's basically a cosine. And you may remember that from your first homework. We need to get into complex mathematics. And why is that? I'll show you in a minute, but let me just go ahead and give you the big picture. Because you're going to regret it if we don't. That's because we're going to have to trade learning some complex mathematics in exchange for future problems being way, way, way easier. Or we could just pretend that complex mathematics doesn't exist and then double and triple the amount of effort that homeworks take. So guess which one we're going to do, right? All right, so, and I'm going to show you a dramatic example right now. Okay, what is complex mathematics? What does that mean? I am assuming that you've seen it, but if you haven't, well, we're looking at it right now, aren't we? The square root of -1 is the letter I right now. Formally, how can there be anything that is the square root of a negative number given what square roots are? Well, it's the letter I, which is an imaginary number. It's technically 1 times I, right? So an imaginary number. Heads up, when you use imaginary mathematics in physical science, things that are observable and thus are real cannot be imaginary. God, that just, I mean, listen to what I just said. Like a kindergartner would understand it, and it sounds like I'm being, kind of like rude, but reality, so what I really mean by that is take our eigenvalue equation. We're using complex mathematics for the wave functions, and here's a way that you know when you do quantum mechanics right, you cannot get like 5I joules. Energy is real. Energy is real in the sense that it's real, and it's real in the sense that there should not be a letter I when you work the Schrodinger equation to get energy. Okay, now it turns out that you may be thinking like, well, then why am I using it? When you do this right, and you get real observables like energy or momentum or angular momentum, and those are the ones we're going to be getting, I will disappear. It gets canceled out every time, divided by itself, something. So that's what to look for. Now again, this is going to give us this is going to make our lives a lot easier. Don't forget simple relationships like this. 5I squared is 25. I squared is minus 25. So there you go. The I is gone. And let's see. Don't forget things like I to the 0 is 1. And I to the 3 would be I squared times I. I squared is minus 1. So that would be minus I. I to the 4th would be 1. Don't forget that 1 over, I think you had this on your homework, 1 over I is minus I. That one comes up a lot. So that's kind of easy to remember. Okay, so what's important about this is, let's look at one of these terms here. What I'm going to do is I'm going to write that in a Taylor series. And if I need you to do this on an exam, of course I will spill out what the proper form is. This comes up a lot. And it ends up being 1 plus the argument squared over 2 factorial, but that's 2. Then the argument cubed over 3 factorial, that's 6. Plus the argument to the 4th power over 4 factorial, that's 24. Let's not worry about it. Okay. So what you now do is, let's collect like terms. Let's put all the real values. Again, the ones without the letter I, that's our new definition of real. So I'm taking care, I've already figured out what to do with all the i's. I've already squared them, if they can be squared. And anyway, I know it's boring just to watch me just read off this. Okay, so there's the real terms. Now let me add, I'm not using the board well, let me plus the imaginary terms. I'm going to factor I out. And so x cubed over 6, right there, minus sign. I'll write one more. X over 5. Notice how it goes plus minus, plus minus. Okay. All right, now it turns out that I know that mathematicians have very rigorous ways of proving this, but if you look up the Taylor series of, guess what, cosine, This is the Taylor series of cosine. This guy, Taylor series of sine. So this ends up being cosine, cos, plus I sine x. Okay, so there we go. Okay, likewise, e to the minus I, handwriting's bad today, minus ix is cos. Now just go through the same procedure. It's just there's a minus. And again, you're not going to see this on any exam. And in fact, what you have on exams, because you probably will need them, would be these identities. E to the ix is cos plus sine. E to the minus ix is cos minus I times sine. So there you go. All right. Now with that said, let me clear the board. Just take me one moment. Maybe that freaking cat will come back. All right. So what about this? All right. Again, I know a lot of you had this on your last homework. What those identities? I don't know if you can see them, but anyway, it's child's play. You know, if you're comfortable with math, you don't really need to write any of this down. Okay, if you do this, what you see is cos plus I sine minus I sine. So the signs cancel. So if I divide that by 2, I get cos. And it doesn't, I don't need to really derive this, do I? Right, there you go. Gotcha. Little I. Okay, that was a weird one. You have to not divide by 2, but divide by 2i. So that one's a little weird. Okay, so now I just said a little while ago that cosine or sine, but I'll stick with cosine, just it doesn't matter. Those cosine or sine is the answer to, geez, actually 100%. Yeah, 100% of our problems for the next 2 weeks or even 3 weeks. Notice that I seem to have complicated it, right? So cosine is simple. You've had that since high school, and this one function is now 2. So it looks like I've traded one function for 2, one that you have a lot of familiarity with and one that you don't. So why would I do that? Okay, tell you what, if you're so sure of that, let me ask you this. Let's look at, now I said before that the Born interpretation says a wave function squared, the absolute value of a wave function squared is a probability distribution. And this is how you use quantum mechanics. You figure out, you write the Schrodinger equation down. The potential energy is the part that makes things different between like trying to describe a hydrogen atom from a helium atom, from a bond, a chemical bond. Okay, so you have all these Schrodinger equations, then you solve them for the wave function, and then you can solve them for energy. When you have the wave function, you can get other properties, which you're going to use the probability distribution mathematics that we had fairly rigorously covered in the Maxwell-Boltzmann stuff. That's how we do this. That is quantum mechanics. That's what this is about. Okay, but if we're always going to do things with probability distributions, we have to take the absolute value squared. Okay, heads up for those who are not very familiar or have never seen complex mathematics. When the letter I has entered the room, the absolute value square, so I've taken the absolute value and squared it, in the world of complex math is the function times the complex conjugate of the function. Now what that means is, again, we have like an I inside of the function. The letter I appears in the function. The complex conjugate has minus I. What you do, and this is not mathematically correct, by the way, what I just wrote. This is like bad. Anyway, but it gets the point across. Wherever you see the letter I, instead write a minus I. Now, if you see minus I already present, then you would write plus I. Or, sorry, let me be more clear. Minus I, which is plus I. All right, let me give you an example. Let me get rid of that. That's not mathematically correct. That bothers me. Okay, so if a wave function is e to the ix, then the complex conjugate is e to the minus ix. All right, it's that simple. So if cosine is e to the ix plus e to the minus ix, then the complex conjugate is just switch it. All right? So I can take complex conjugate of things like cosine. It doesn't make sense until you do something like this. Notice that it actually didn't change it, right? Oh, sorry. Notice that it didn't actually change anything, which makes sense because cosine is inherently a real function, right? Let's see, that's just kind of a neat thing. All right, so what am I babbling about? So let's say, let's actually go back to this example here, e to the ix. And now I've shown you some complex conjugates. Let's do this. So let's figure out the absolute value squared, which is the wave function times its complex conjugate. Now let us work in a world where we never decided to use complex mathematics. So we have to use those things up there. I'm sorry if you can't see those, I can't tell. Okay, so what is this? This would be, oh, this sucks. Okay, so I had to think about this for a second. Let me look up there. Okay, so what you're going to get cos squared x. Then you're going to get I sine x cos. I'm kind of doing this in my head. I cos sine. And then you're going to end up with I squared sine squared, which is minus sine squared. Okay, and let's see, what do we got here? No, wait a minute. No, one of them has a minus sign, right? So, let's see, that means I'd have that. Okay, so it would help if I did this right. Sorry, I should have written this down. I should have written that down first. Anyway, so when you get, okay, those cancel, and you end up with cos squared plus sine squared, which you should know is 1.0. And I also, just in case, if this comes up on an exam, I will actually even give you that identity. I would hope that you would know that, but if you don't, it's okay. You have that identity. All right, so you just saw me struggle with this. You saw me make a mistake. You saw me not even work the problem that well. Let me show you this. Let's do this a different way. Let's do this using complex mathematics, specifically e to the ix. And I just showed you that the complex conjugate is e to the minus ix. Now, in case you have this on an exam and you're not sure what to do with this, look for an identity in the cheat sheet, because I give you all the identities that you will ever need, even ones that I would really hope that you know, but remember, you can always check with your calculator. So so this is the problem, and now you don't know what to do with it because you forgot some of your math. Look in the cheat sheet, and you see this identity. If, however, you are freaking out, type e to the 3 times e to the 7 and check whether it's e to the 10. Right? That's how you would do this. Or just even check the identity if you're really freaking out. All right, so what does that mean? That means that this is e to the ix minus ix, which of course is e to the 0, which is 1. Oh, look how quickly it took me to... That was a billion times easier. Heads up. we're going to have a function e to the ix, sine x, cosine e to the tangent of x. Square that and integrate it. Okay, that was extreme. It's not that bad, but you get my point. We are going to have wave functions that are significantly more complicated than this. And when you square those things, and you can get rid of all the ix's, you're going to want to do that. You're going to want to do it this way, not this way. This way, forget it. You will algebraically get lost, and you will miss the question. You do it this way, come on. I mean, look, this was stupid. This was stupid easy, right? So, with that said, I see I have about 7 minutes. I want to just review a little bit about wave functions. So let me wipe out the board. Okay, so last bit, and we're going to be done with wave functions, is there's a couple of rules about wave functions. These are not perfect. One or two of them are, one or two are not. I'll make it clear what's what. So again, there are 4 stipulations on wave functions. That's what I'm going to write down. Okay. One is that you cannot do this. They cannot, oh, let me exaggerate that. There, that's better. They can't loop back on themselves. Right now, why is that? Well, let's look at the wave function. Let's pick a point and see what you got. At that particular position, you have, call that x naught, you have 3 values for the wave function. Since wave functions squared are related to probability, it's fair to say that the particle has 3 probabilities of being at that position x naught. No. No. That's impossible. You can't have 3 probabilities for being, for anything. All right, so we can discount that quite easily. Heads up, maybe I'll put that on the exam and say, hey, what wave function is wrong and say why. And that's related to the fact that it's a probability distribution. Okay, number 2. This is not, okay, this one isn't 100% correct. But with that said, the wave function, I'm going to write this down, must be smooth and continuous. Okay, let me do smooth. Let's see. One example of smooth. One example that is not smooth, right? So let me give you an example of what is not smooth. That would be like a wave function at, I'll always pick x naught on the x-axis. Everything will be on the x-axis for a couple of weeks. Okay, so that's a wave function that does this, like flies off to infinity. So it's like got a sharp point, right? I tried to dash that to make it clear that it goes up and down. It doesn't look too good, does it? Anyway, okay, no good. Now, why is that? It turns out that if you have a sharp point in a wave function, another example is if the wave function, let me give you another one. If the wave function suddenly increases at some point, just like I did here, then what happens is, think about a double derivative at an infinitely sharp point, like a singularity. What's the double derivative? Well, it's technically infinity. Okay, we know that the double derivative is related to kinetic energy. So for this particle to have this wave function, it means that the particle has infinite kinetic energy. So no, that doesn't work. So you don't expect sharp points in your wave function, so that fails the smooth test. Okay, continuous would be, that's actually also an example of continuous, but let me draw an example. Okay, so again, this is not continuous, right? And that would be something like, like this, where there's this jump. Now, the reason that would be is actually for the same reason that you have here. You would technically have two different values for probability at the same point. So in this kind of exaggerated example, I have 3. In this example, I would have 2 probabilities at this point, x naught. Again, no, that just inherently doesn't make sense, so that's not true. Okay, the last one, next to last, the wave function cannot be 0 everywhere. Okay, that one is stupid. It's stupid. The reason is that what they're referring to is the eigenvalue equation, which is the Schrodinger equation. Technically, the wave function being 0 is a solution, but it's a stupid solution. Of course, 0 equals 0, but that doesn't get you anywhere. So I don't know why anyone includes this. I mean, obviously, no. You remember, like, solving x plus y is 1, x minus y is 2. Remember those couple linear equations that you can solve, like with matrices? And everything being 0 is always a solution, but not the one that you were supposed to find. The same thing is happening here. Okay, so that's kind of silly. Okay, the last one, and this one's kind of important, and I'm not using the board too well, but let me point out, this is one I like to say for last, and this is where you get the quantum and quantum mechanics. And what it means is, here, let me give an example. Okay, so number 4 is you need realistic energies. Okay, now you get the energy from, you have a wave function, you use the Schrodinger equation to get the energy, all right, but it has to make sense. Now let me give you an example, and as I've hinted to many times, the particle in a box problem, which goes from 0 to L, as usual, or in the x direction. And what happens is that the potential energy outside the box is infinitely high. Okay, so it's a trap. So what that means that the particle cannot escape the box. It cannot be to the left of 0, it cannot be to the right of L. The reason is that the energy would be infinite. How else can it smash through an infinitely high barrier unless it had an infinite amount of kinetic energy? That would work, but again, just like you can't have a sharp point, no. Now, here's the neat thing. We're getting to this. I'm just previewing. It turns out that this requirement is where the quantum and quantum mechanics comes from. It means that not any energy will work to solve this problem. To solve, I mean wave function. Let me give you an example. If I start looking at wave functions as a function of energy, what I find is that there are some that are special. One of them looks like this, right? It's a wave, it's a half wave, and it has nodes. In other words, it's 0 at x equals 0 and x equals L. Perfect, right? It doesn't penetrate outside because the wave function turns to 0 at the left and right barrier, and that corresponds to a certain energy. Now, if you look at higher energies, that will get violated. The wave function goes into the barrier, which is not allowed. But then, as you go higher and higher in energy, what you do is you find another wave function that has nodes at the boundaries, and it looks like this. So again, the wave function has a node at x equals 0 and a node at x equals L. Since it's 0 at the barriers, it doesn't penetrate outside, and therefore that wave function at that energy is a solution. Notice that there's a discontinuity in energy. This is a low energy, and then the next state that's allowed in this trap has a higher energy. And the difference in energy is some, it's like a joule or something, or an electron volt. That means that if I was to do spectroscopy on this particle in this trap, I would see, let's say electron volt, I would see it absorb 1 electron volt of energy, which would be like an infrared type of transition. 2 electron volts would be red, and 3 electron volts would be technically blue. So, depending on the difference in energy between these 2 allowed quantum states, I would observe different types of spectra. That is where the quantum and quantum mechanics comes from, this particular stipulation. Anyway, I'm sorry, I'm probably gone over. Sorry about that. This is everything you need to know about wave functions, and next time we're going to do some reviewing and we're going to start talking about operators. All right, I will see you all on Friday.